Okay, welcome to another OpenStax astronomy video. We'll be looking at chapter 23, the death of stars, and we'll look at both low mass and high mass stars. So we'll start off with the death of low mass stars, and we talked about how it moves throughout the HR diagram, leaving behind a planetary nebula and then into a white dwarf. And so we'll talk more a little bit about what that corpse of a white dwarf actually is. So here's the HR diagram, and as we had discussed, when it becomes unstable towards the end of its life, the star tends to swell up, and then eventually it will turn into this planetary nebula, dispersing all of its remaining gases. And then what will be left behind is a white dwarf that will cool off, and it will lower in temperature there. So here's an image of a white dwarf, and what keeps it stable is going to be degeneracy pressure. So similar to that of a brown dwarf, we see that atoms can only be contained to such a small amount of space. So it's not gas that's pushing back on it now. It's that degeneracy pressure of those atoms pushing back themselves. And so here we need to see it in X-ray. Because that white dwarf is very, very faint, and so we need a different part of the electromagnetic spectrum to be able to detect it there. And here we see a binary system. The size of a white dwarf, something like our sun, will end up being about the size of the Earth. Something with a little bit more mass will end up being a little bit smaller because it's more mass, so that gravity is going to contract it just a little bit more. And so the Chandrasekhar limit here is about 1.4. We had discussed this before, but that's what we call the white dwarf limit. Anything a bit more massive, those electrons would just move close to the speed of light, and so nothing could exceed that. So this ends up being the limit for white dwarfs. So the death of high mass stars, and we talked about how they turn into neutron stars. They have that advanced burning, which makes them able to create heavier elements, but becomes more unstable. And then you end up with a large explosion of a supernova, leaving behind that neutron star. And so here are some 5 different supernova explosions in other galaxies here. And so pointed with the arrow, and then you could see how bright it actually is, right, compared to that entire galaxy. So we're looking at things that get extremely, extremely bright here. That energy that's released, instantly is more than energy that our sun will create in its entire lifetime. Here's an image, again, with some coloration added to see the different gases there of a supernova. And we could see that extending out, the gases being pushed outwards there. So this will lead us into pulsars. And I'll kind of let the cat out the bag here. In short, pulsars are neutron stars. They were discovered differently, and so pulsars were thought to be something differently, but then eventually we found out that they were one and the same. So a neutron star is a ball of neutrons that are left behind after a supernova. Again, degeneracy pressure keeps that stable. And a neutron star will be about the size of a small city, so about the size of Long Beach or so. Again, a white dwarf will be about the size of the Earth. Here we're talking something extremely small, right? That mass is contracting and very, very tight, so probably about the size of Long Beach. When we discovered these pulsars, what we saw was that we saw this intensity coming out from them. And these peaks occurred very frequently, so very precise. Here was one that was 1.33730 seconds apart. And so it was kind of like a beacon in a lighthouse that kept spinning round and round. And so here we kind of see an image of that. And so these pulsars, very, very small, are rotating extremely, extremely fast here. Creating that large magnetic fields as well, but we see those kind of beacons of radiation. And so it creates kind of these accretion disk around a neutron star, and so what happens is you get these large bursts of X-rays that typically end up happening. But we saw with these pulsar stars here, so these pulsars, that when we looked at them, we were getting those frequencies, right, rotating time and time again there. And ultimately what happened is that the speed at which they were rotating, we're talking velocities about, 20% the speed of light. Anything else apart from neutrinos would fall apart. So anything else would just be torn into pieces. So these pulsars had to be these neutron stars. And so let's talk now a little bit about evolutionary of binary star systems. And so when we talk about white dwarfs, if they're in a binary star system, mass from the other star could fall into the white dwarf, creating these accretion disks. And so matter will start orbiting around, coming towards the inside. And those accretion disks end up getting very, very hot, where it could spark. So those temperatures get hot enough for that hydrogen fusion. And what we end up with is a large explosion, what we call a nova. So not a supernova, but a nova. So a white dwarf with a companion star stealing some of its matter, and then a hydrogen fusion happening in the accretion disk. And so what could happen is that in a nova, everything there'll be an explosion, but the white dwarf will be left intact. If it steals more matter, it could also have a supernova, and that would make the white dwarf completely disintegrate. So, two types of supernovas: those from a high mass star where it explodes, and then a white dwarf supernova, which is getting matter from a binary star, okay? So two types of supernova, and then a regular nova as well. And here we see the light curves of a massive star supernova and a white dwarf supernova. So very, very intense with those white dwarf supernova, that initial explosion there. And so similarly, we see that neutron stars could also form accretion disks, just as white dwarf binaries. So they're able to collect material as well. And so what happens with these neutron star systems? Well, we see that they have these large X-ray intensities, these kind of big gamma bursts. And so the accretion matter here, and this slide was actually in the wrong place before. This is where it should be. So the accretion in that neutron star spins extremely, extremely fast, and it causes episodes of fusion, and so it leads to these X-ray bursts. So that leads us to these gamma ray bursts here. If we do a survey of the Milky Way, we see that these actually occur throughout, kind of universally throughout the galaxy here. And here we could see this image of a gamma ray burst, kind of the afterglow on that image on the right there. So we could see these are extremely, extremely large. So we see a lot of these gamma bursts with those neutron stars that throw them out. We've also seen these with two neutron star binary systems that merge together. And we've also seen these large gamma ray bursts when we see black holes forming. So these are probably the most energetic bursts since the Big Bang. So a lot of energy being displayed there. And we'll talk more about the death of high mass stars. So we talked about low mass stars, high mass stars, and really anything beyond 3 solar masses will collapse onto itself and form what we call a stellar black hole. And so that's really one of the ultimate fates of stars as well. And we'll discuss that a bit more in the next module, because that's more of a cosmology topic. So low mass stars ending their life as white dwarfs, planetary nebulas and white dwarfs. High mass stars ending their life as supernovas, then neutron stars. But there's another ultimatum for high mass stars, which will ultimately end their life as a black hole.